This video is designed to go with section 15.2 from the Musser Math for Elementary Teachers book. So what we're going to take a look at is the difference between the slope-intercept equation for a line and the point-slope equation for a line. And we're going to start with point-slope because point-slope is actually a little bit more versatile than the slope-intercept equation. So first we're going to go back to what we already know from a previous video. We already saw that slope can be calculated by y2 minus y1 over x2 minus x1, or the change in y over the change in x. If I do a little bit of algebra here, and I multiply both sides by the denominator, x2 minus x1, which means I multiply this side by x2 minus x1, I will wind up getting m times x2 minus x1 equals y2 minus y1. Why is this so important? Well, it turns out that if I know one point and the slope, then I will be able to find any other xy pair that would lie on this line, and that takes us directly to the slope-intercept equation. So, in other words, I could totally take off the x2, y2 because I wouldn't need to find that other point. That other point could be anything. And so if I remove the subscript of 2 from each of those values, I now have an equation for a line, because this will give me any x and any y, provided that I know m, which we already know is our slope, and provided that I know an x1 and a y1, which can be any point on the line. And because we don't want a y minus y1, we could add the y1 over to this side. Again, it's a little bit more algebra. And so I can basically come up with what's known as point-slope form, which is y equals m times x minus x1 plus y1. The reason that this is more versatile, I mentioned before, is because this works for any x1, y1 that could possibly be on the line. Now, there's a very specific form for a line that you probably remember from previous algebra classes, and that's called slope-intercept form. And slope-intercept form is our good old y equals mx plus b, where m is still going to be our slope. We're never going to change what m means. But b is going to be the y value of the y-intercept. Now, if you don't remember what the definition of the y-intercept is, the y-intercept always has an x value of 0, or in other words, it is the point where the line crosses the y-axis. That's by definition. So this is the point where the graph crosses the y-axis. And it occurs when x equals 0. And that should make a lot of sense, because if you're on the y-axis, then that means you have not moved in the x direction. And so x is going to have to be 0. So let's just prove why that is the y-intercept. So let's say we have y equals mx plus b. Okay, so it's general. We're not plugging in any specific values. But I want to know when x equals 0. What am I going to get? So if I plug in 0 for x, it doesn't matter what the slope is, because what's anything times 0? I'm going to get 0. And so I'm going to get a y value of b, which proves that I'm always going to get 0, comma, whatever b is as a point on the line. And that's why this is your y value of your y-intercept. M always designates your slope, because that's how the graph is changing. And again, if you just refer back up to the point slope formula, you can see how we use the slope formula to even get that form of a line. The other neat thing, and the reason why point slope form is again more versatile, is because point slope form will simplify to y equals mx plus b when values are plugged in. So there's really no need to have to jump to y equals mx plus b, especially if you don't have the y-intercept, which you may not always have, and so it's nice to have another alternative.